Let's look at a few application problems for quadratic functions. So here we have a graph. They've given us some of the key points on that graph. And instead of starting with an equation, we're going to start with this image of the graph to try and pull out the characteristics, right, to describe some more about this quadratic function. So direction of opening, right, we don't have an a value here to compare it to, but we can see the direction that this parabola opens. And because it's like a bowl shape, right, because the rest of the lines travel upwards, this opens up. When we're looking for our vertex, well, they have so nicely pointed out our vertex for us. Remember, the vertex is this point here down at the bottom, or if it opens down, the point at the very top. So my vertex is 0, -4. Remember that my axis of symmetry, if I wanted to talk about the symmetry of this graph, well, the line of symmetry would run right down the middle here. And because it's a vertical line, we describe that as an x equals, right? Because all of the points along that line have the same x value in common. And we always use the x coordinate of our vertex. So in this case, we're using 0. Our x and y intercepts, well, they show us two x-intercepts here, right? Any of these points where our graph intersects that x-axis, so -2, 0, and +2, 0, those are our two x-intercepts. And our y-intercept happens to be the same as our vertex, and that's okay. My y-intercept, again, just the location where x is 0, where I haven't moved left or right from that y-axis, -4. Right, a point can do double duty. It can be a vertex and a y-intercept, or a vertex and an x-intercept. Or my x and y-intercept can be the same point, or on the origin. Talking about domain and range, again, this, just like every other quadratic, I'm going to say that x can be any real number because we know, right, while the graph doesn't have arrows, we know it's going to keep going left as it goes up on the left side, and it's going to keep going right as it goes up on the right side. Our range, again, is every point from our minimum, right, our vertex in this case is a minimum, and every point above that. So I'm going to say that I have y values that are greater than or equal to -4, that minimum value there. And then I just want to specify again that those are real numbers. Now, A, B, and C, we don't have the graph here, so it can be a little tricky. The main one we can find here is C. C is going to be -4. That comes from our y-intercept. And A, we just know that A is a positive value. We don't need to know much beyond that. Let's talk about some real-world problems now. So we have a situation here. A frog is sitting on a rock, and then it jumps into a pond. Its jump can be modeled by the function we have here, where h is the height in centimeters above the water, and t is the time in seconds. So no, a lot of the time we talk about functions as f of x, meaning f tells us it's a function, right? Every x relates to only one y, and that it's a function in terms of x, that x is our independent variable. Here it's telling us that this thing is still a function, but our dependent variable, the y value in this case, is height. So this is our y value. And then because it's h in terms of t, t is that independent variable. T is like our x value. So we can graph it exactly the same. We're going to pull up some technology and look at this graph. All right, so after plugging this into my graphing calculator, here's what this situation looks like. I've chosen some specific window settings, right, just to fit this better in my graph. It was a pretty narrow graph, right? We noticed by that 490 in front of our t-squared. So I only went from -1 to 1, and then I changed my scale to 0.1 so that I can see a better idea of where these x-intercepts and points might be. And because my y-intercept here, And we're kind of getting ahead of the boat. My y-intercept is 25. I knew that I had to make my y maximum something bigger than that, so I went with 50. Again, your window settings can always change a little bit. Just make sure you've adjusted it so you have a good view of your parabola, right? You can see the vertex, you can see the x and y intercepts, and you don't have too much empty space around it. So, graph the function and sketch. We have graphed it. Let's create our sketch, but let's do that by finding some specific points. So I'm going to find we can do y-intercept first, even though we already know this. This is at 25. And I want my sketch to match what I'm seeing here. So I've changed my axes. So you are by all means welcome to put your axes wherever you want, right? That just means that this is -1, this is +1, and because I've changed my scale, right, each of these boxes is going to be 0.1. So I'm looking at my calculator. I'm going to find some more points. Let's look at these x-intercepts next. So one at a time, I'm going to pick some point to the left. Right, these tick marks can help me with this step too, because I know that like -1 is the far left side of my graph, so I can type that in for my left bound. And then if I want to go right of this first x-intercept, as long as I'm picking any point before like over here, right, 0.4-ish, if I put 0, right, even though my two lines are pretty far apart, my x-intercept is still between them. So -0.12, let's say. So we know it's just after -0.1. So there's 1 point for us. Let's go to our next point. Let's do the same process again. 0. Now left bound I can put 0 because I know that I'm now just going to go left and right of the x-intercept on the right. Right bound I know I could put all the way up to +1 because it's somewhere in between there and the edge of the graph. And it says it's 0.43 if we're rounding that to the nearest hundredth. So again, I know because I chose my scale, each of these boxes is about 0.1. So I'm going to go about 4 boxes over 0. My y-intercept was at 0.25. Now I made each of these boxes 5. That was my scale. So I'll go 5, 10, 15, 20, 25. And then the last point we want is our vertex. Remember, this one's going to be a maximum because my graph opens down. This vertex point up at the top is the maximum point. And again, left bound, right bound, I can type numbers in, I can use the blinking cursor. As long as I'm picking somewhere left and then somewhere right of my vertex, it's going to tell me essentially what's the highest point between these two lines. And so it's 0.15, 36.48. 36.5. So 0.15, I'm going to go about 1.5 boxes over. 35, going to be right about here. All right, and we're just trying our best to sketch. We're trying to represent it as accurately as possible, but we know it's not going to be perfect. All right, so there's our sketch. So find the y-intercept. What does that represent? Well, our y-intercept was 0.25. But remember that x and y in this case was representing h and t, or sorry, t and h in that order. So if 0 is t and 25 is h, what does that mean? Well, that means at time 0, right, when I haven't started counting this frog's jump yet, they were at a height of 25. I might want to say something along the lines here of initial height is 25 centimeters, right? Or another way to think about this is the frog was jumping off the rock. This is telling us the rock is 25 centimeters tall. Right, thinking about the context, thinking about what this situation means, if our x-axis is representing time and our y-axis is representing height. What is the max height the frog reaches, and when does it reach that height? Well, that word max should be your hint that you're looking for your vertex here. And again, that vertex point that was, let me copy that down, 0.15 and 36.48. So again, what is the max height? Well, we're looking for the y value. So we have a max height of 36.5 centimeters. And when does that happen? Well, that happens after 0.15 seconds have passed. When does the frog hit the water? Well, we're looking for our x-intercept here. Specifically, I'm looking for this second x-intercept, because we're looking for a time in the future. We're not looking for a time in the past. In this case specifically, negative times don't really make sense for us. So we're looking at a time in the future. We're looking for an x-intercept because that is the water level, right? A height of 0 means they're at the water. So the frog hits the water at 0.43 seconds. How high is the frog 0.25 seconds after it jumps? So our t value is 0.25. When it's asking us how high, we're trying to find the h that relates to that. So there's a couple things we could do. We could plug this value of t back into that original equation. Right? If I substitute t for 0.25 here and t for 0.25 here, right, it's telling me h. I can solve for my unknown. But our calculator does this kind of work for us. We've seen that before. And that's actually under our value button. So if I go to calculate and I choose value, most of the time we just choose 0 because that's our y-intercept. But we can actually choose any value of x. So if I choose a value of 0.25 for x, it's going to tell me that when on the x-axis I'm at 0.25, what's the y value where my parabola is? And it happens to be 31.88. Oops, wrong pen. 31.88. And again, including units, because this is a value that means something. It's not just an arbitrary number. And the last thing, what is an appropriate domain and range? So we're concerned about the domain, right? In this case, being careful, our domain is talking about t's now instead of x's. And our range is talking about h's now instead of y's. So we want to be clear with that. So my domain, we have t such that. And then here we want to think about the situation. When it's asking us for the appropriate domain, it's saying what part of this actually makes sense. If we're actually picturing a frog jumping, is this poor frog going to be stuck in this parabolic shape for the rest of his life? Does he jump up in this parabolic shape, right? He like shoots out of the water, he jumps up, he starts to fall, and then he's just going to keep falling at that same angle for the rest of his life? No, probably not, right? And does it make sense to talk about the time before the frog got to the rock? No, because he probably didn't follow that parabolic path, right? If we look on our graph, this green spot, this is the start of the jump, and then this is the end of the jump. So he follows that shape all through his jump. But he probably like hopped his way up to the rock and he didn't follow that black parabola that we had sketched. And when he hits the water, he's probably going to swim off and then jump back up onto land. So we actually only care about the segment of this graph from 0 seconds to 0.43 seconds. I'm going to sandwich my t in there. I'm saying we're looking at times that are bigger than 0 seconds, but also smaller than 0.43 seconds. because I don't think any time outside of this domain will actually be modeled by this parabola. And then our range, the same idea. I'm only looking at that jump portion. I'm only looking, and I'll highlight it for us, at this section here. So I only care about the range for that section as well. The lowest the frog goes there, so I say h such that, well, we only care about the height that's above the water, so greater than 0. And then we see that from there, the frog only goes up to a maximum height. When I'm looking at that, right, I'm looking at my vertex, 36.48, right, or 36.5. That's the highest my frog goes, so I don't have any values above that. And so that's our domain and range in a contextual question. And that's how we can find all these values and relate them to a real life situation, relate them to a real context.